Hello students, welcome to lecture 25 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on Metamaterial Perfect absorbers. So here is the lecture outline. We will first look into what are these Metamaterial Perfect absorbers, and then look into the classifications like narrowband perfect absorbers and broadband perfect absorbers. We will also take an example of ultra broadband perfect absorber, and then we will see the applications of these metamaterial perfect absorbers, or MPA in short, and their application in solar energy harvesting and as thermal emitters. So when we talk about metamaterials, the first thing that comes to our mind is that these are basically artificially engineered structures. So where the unit cell is designed in such a way that can give rise to some extraordinary properties which are not found in natural materials. And the first thing that comes to our mind will be the negative index material, right? Negative refractive index. But that is not all. When you think about other applications of metamaterials, one most important application is towards light absorbing. Now light absorbing by any artificial structure has always been a matter of research, because you want to maximize the absorption. Like why you need that? Like if you think of a solar cell where you are harvesting solar energy, so you want to absorb the entire solar radiation that is falling on the solar cell. You do not want anything to be reflected. What goes back is actually a waste. So you are not efficient if you are not able to capture all of the solar radiation coming towards you. Similarly, a photo detector or any other such devices which are supposed to harvest light, you want them to first act as a perfect absorber so that you can absorb that, okay, and then you can convert that absorbed energy into some other form. So light absorption is another eye-catching characteristics of these artificial structures which are metamaterials, and the metamaterials with near perfect light absorption are known as these metamaterial perfect absorbers, MPA. Okay. Now in order to realize perfect absorption, reflectance is suppressed. And how do you do that? You do that by matching the effective impedance of the metamaterial to that of the incident medium. So whenever there is no impedance mismatch, there is no reflection. And when light falls on an interface, there are three phenomena that takes place. One is reflection, one is absorption, the other one is transmission. Okay, so you have to somehow, in absorbers, you want the entire light to be absorbed. So you are trying to cancel the reflection by using some metamaterial absorber, and also you are trying to get rid of the transmittance, and that you can do by introducing another metallic plate which acts as a mirror, or by using similar mechanism that we have seen in the multilayer system. So metamaterial perfect absorbers, they do not have any transmission, they also do not have any reflection. So whatever falls on them should get absorbed. Now what do you mean by perfect absorption? So we typically call a perfect absorber when it is close to 99% absorption, okay, and it remains highly absorptive over a wide range of incident angle, okay, for both TE and TM polarizations, okay. So if you recall our previous discussions, at larger angle, at glazing angle, you usually have larger reflection, but in that case your light will not be that strongly absorbed. So at larger angle there is a possibility of absorption to get reduced than 99%, but still it should be like at least more than 95% or so, okay. So what do you basically take to make this kind of absorbers? Now when I tell you that this material is lossy, the first thing that comes to your mind is that okay, this is a lossy material, so it's not very good for waveguiding because there is high loss. Also it is not a very good material for creating a resonator cavity because it will have low Q because it is a lossy material, so the full width half maximum will be large. But then lossy materials are useful, very useful in case of metamaterial absorbers, because these materials can then significantly enhance the efficiency of absorption. Okay. So recently Metamaterial Perfect absorbers have grabbed a lot of attention because of their near unity absorption capability over narrowband or broadband. Okay. So that takes us to the classification of this Metamaterial Perfect absorbers. So as you can see, based on the wavelength range they cater to, you can categorize them into two buckets: narrowband Metamaterial Perfect absorbers, and then you also have broadband Metamaterial Perfect absorbers. So if you carefully look at the narrowband structure, here you see figure A, you can see that these are basically overlapping rings and a column, and there is a gap between this column and the center of the ring, that is called delta x. So when delta x equals 0, you get almost like 90% of absorption, right, in this particular case. When you change delta x to 200 nanometer or so, you get almost 95-99% of reflection, okay, sorry, absorption. When you further increase it to 270 or 350, what is happening? The resonance is even getting sharper, so you are getting a high Q absorption peak and you are closing towards that perfect absorption mark, which is very close to unity absorption, right. So this is typically what I am not going to describe immediately the physics behind this, okay. These are kind of symmetry breaking high Q modes, okay, and I'll just look into the features here because this is the narrowband. We'll see in this lecture only how to develop a structure that can give you a narrowband Metamaterial Perfect absorber, and we will also look into this particular structures which are able to give you broadband Metamaterial Perfect absorber. So here you can see that it is basically a broadband absorber. So you can see it ranges from 3 to say 5.5 micron, where the absorption is maintained over say 95 or 99%, like that. Now what are these three arrows showing here is that at different regime, different portion of the structure is playing the role of absorbing the light that is falling onto the structure. So here is the structure. This is basically a this is the tapered shape, okay. You can also call it tapered tooth kind of a structure. So at different wavelength, different part of the structure is resonating, and that is able to absorb the electromagnetic radiation. Here you see at short wavelength, the top portion of the structure is absorbing most of the incident electric field, magnetic field, okay, and at longer wavelength, the bottommost part of the structure, which is the widest portion of the structure, is responsible for the absorption. Now let us look into some of these techniques of how do you design narrowband metamaterial based perfect absorbers, okay. So here is the schematic. So you need metal, lossy metal to design absorbers. So here is a schematic of a 2D array of gold discs, okay. So the diameter is 352 nanometer and the thickness is 20 nanometer, and the periodicity along both x and y directions are 600 nanometer. Then there is a spacer layer below this gold discs, that is MgF2, that is magnesium fluoride, and it has got a thickness of 30 nanometer, and then you have a gold mirror which is 200 nanometer thick. So this is basically that portion which is completely cancelling out any chance of transmission through this structure. So 200 nanometer gold film behaves like a bulk gold film. It is giving you zero transmittance, and it will be able to act like a good mirror. Okay, and this entire structure is placed on top of a glass substrate. Now you can make narrowband MPAs, okay, metamaterial perfect absorbers, for which the top metallic layer is either patterned or unpatterned. So here we are taking a patterned metallic layer. Okay. Now in this case, what we are using, you are using a normally incident light with X polarization. However, X and Y polarization hardly make any difference here because the structure is symmetric along X and Y, right? And you have taken the permittivity of magnesium fluoride as 1.9, and these are the parameters that describe the bulk gold permittivity near the near infrared wavelength range. You can use Drude model with a plasma frequency of 1.37 into 10 to the power 16 hertz, okay, and damping constant is this one. Okay. So with that you can figure out that when, so these are basically simulated reflection spectrum which is plotted when the damping constant is considered to be 1 times, 3 times and 5 times of the bulk gold. So here you see when you are basically, there is significant difference in the reflection spectrum or reflection dip, okay, and you can see that when it is 3 times, when the damping constant is basically 3 times of that of the bulk gold, you are able to get negligible reflection, okay. So it is 0.28%, okay, and this is a scale up to 1, so you can understand. So this is basically 0.0028, so it's almost zero reflection, right? And as I told you, in this perfect absorber, A is basically calculated from what is reflected and then what is transmitted. These two are taken out from 1. So because of this bulk gold, there is zero transmission. So if there is no reflection, the entire thing is getting absorbed. Okay. So here it shows that reflection with zero intensity is achieved using a damping constant that is equal to 3 times of that of the bulk gold. So that actually tells us that what should be the ideal thickness of those discs. Okay. So if you are able to use very thin discs, so you can actually get this high damping constant that can give you this perfect absorption. So that is where the design of this metamaterial comes into picture. At resonance, a strong enhancement of the localized electromagnetic field takes place between the two layers, the two metallic layers. So there is a gold disc and then there is a gold film, and in between there is a thin spacer layer which is the dielectric. So this electromagnetic energy can be efficiently confined in this intermediate spacer layer, and that ensures that no light is reflected back. So you are basically trapping the energy. So this gives rise to profound reflectance dip in the spectrum with nearly zero intensity, and that in turn gives rise to nearly 100% absorption. So in fact, this kind of devices work as perfect absorber over a wide range of incident angles. Now, to better understand the nature, what is happening in this particular perfect absorber, we should look into the current distribution at resonance, which was simulated, and this is the figure that shows that. Okay. So here you can see that there are basically anti-parallel current distribution in the gold disc and the bottom gold layer. So here it goes like this, and here it is like this. So you can think of a circulating current like this, and this is basically can be thought of as a magnetic resonance which comes from the circulating current, and this current basically results in a magnetic moment which strongly interacts with the magnetic field of the incident light. Now at resonance, what will happen? A strong enhancement of the localized electromagnetic field is established between these two layers, okay, and that is the reason why you will be having a trap of energy in this magnesium fluoride spatial layer, and no light is going back. Now, the simulation study has also been conducted to see the angular dispersion of the absorption peak, because right now the peak is very attractive. It is giving you almost 100% absorption, but you have done only for a normal incidence, that is theta equals 0. Now, when you do the different angle for both the polarization, these are the plots that shows you with frequency and angle how the absorption peak is changing. So, this is for TE polarization and this one is for TM polarization. So, if you look at the TM polarization first, the one on the right, the absorption peak is seen to be nearly independent of the incident angle. So, here on the y axis you are varying the incident angle, so it varies from 0 to 80 degrees, and here you see that more or less it is independent of the incident angle. Then that is amazing, and even at 80 degree you are able to, at the same wavelength, you are able to hit almost 80% of absorption, sorry 96% of absorption, and that is tremendous, okay, that is really working well. And this is because of the fact that the direction of the magnetic field of the incident light remains unchanged with various incident angles, and it can effectively drive the circulating currents at all angles of incidence, and that is why for TM polarization you hardly see any difference. However, when you look into this particular figure on the left, the contour plot here, the magnetic field cannot drive the circulating currents efficiently at very large angles. So, anywhere above 50 degree or so, you see the absorption has dropped significantly, okay. So, at 80 degree you actually land up having like 50% of absorption. So, that is a lot of drop from the perfect absorber to that. So, this is one study that tells you how to design metamaterial perfect absorber, and always remember that when you change the size of the disc and the periodicity, that would help you tune the position of this absorption peak, okay. Right now it is shown at a particular wavelength, and it is, or it's in frequency scale, so it is close to say 188 terahertz or so, and if you change the periodicity or the size of the disc, you should be able to tune that, okay. So, that is how you can design application specific narrowband perfect absorbers. Now, moving on to the broadband perfect absorbers, let us see how you do that. Now, the name itself tells you that you are designing something broadband. So, you should have kind of a possibility where you can cater to multiple peaks that can overlap spectrally, and that can give rise to this broadband nature, right. So, broadband, definitely you are catering to a much wider wavelength range right now. So, here is the schematic of that broadband absorber, but surprisingly it is more or less similar kind of a structure, but then here the material property is different. You are basically using a titanium disc, okay, on top of a gold film with a silica layer on the top acting as a spatial layer, right. So, this particular schematic shows a broadband polarization insensitive and omnidirectional absorber working in near infrared range. So, that is the range here it has been targeted to, and it is based on a simple traditional metal dielectric metal or metal insulator metal configuration. So, here what happens, the highly efficient absorption is mainly coming from the excitation of low Q localized surface plasmon resonance which are supported by the titanium nanodiscs, and you are also generating the propagating surface plasmon resonance in the interface between gold and gold film and silica. So let us look into the spectral characteristics here. So this is the black line shows experimental result, and the dotted line over there shows the simulation result, and they are matching very closely, and you can say this is like a perfect match between simulation and experiment. So here you can see that under normal incidence, so here we are only considering theta equals 0. Okay, the measured absorption of this fabricated sample is over 90% in the spectrum ranging from 900 to 1825. So this is the range till which it is more than 90%. Okay, so this is the experimental one, and when you do COMSOL multiphysics numerical simulation for the same structure, you also see very similar result. And in the simulation, you are basically considering a single unit cell which has got periodic boundary conditions on both sides to repeat it in both x and y direction, and that can give you this particular structure. Okay. So numerical simulation also shows that it is very close, and because the structure is symmetric along x and y, so it will be independent of the polarization of the incident light, and you can get very high absorption when the incident angle is less than 40 degree. So beyond that, there will be drop in the absorption. So here are some simulation results that shows you how it works. Okay, so to reveal the physical mechanism in the perfect absorber, you can actually plot the electric and the magnetic fields, okay, at the two absorption peaks. So if you carefully see that there is basically one peak and then there is another peak here. Okay, so there are basically two peaks which are spectrally overlapping. One is a narrow peak and another one is a pretty broad peak. So there is a peak at 914 and another one at 1468 nanometer. Okay, and if you look into the electric field distribution, these two resonances both look like electric dipole resonances, okay, on the nanodiscs when you are considering the TM polarization. However, the magnetic field distribution that you see here is pretty different in these two cases. And if you also analyze that what is the origin of this peak, then you can say that the short wavelength resonance that you are seeing at 914 nanometer is basically considered to be the propagating surface plasmon PSP, okay, resonance that comes between the continuous gold film and the silica spacer, where the magnetic field is not only strongly confined in the gap region between the nanodiscs but also strongly enhanced between the nanodiscs. And the other case, which is the long wavelength mode, so at you can call this as lambda 2, this one is lambda 1. So you can say the long wavelength mode, which is at lambda 2 1468 nanometer, this is basically a localized surface plasmon resonance peak where the magnetic field is mainly concentrated within the gap between the topmost nano antennas and the gold underlay. Okay, and since titanium is dispersive, it's very dispersive and has a relatively large imaginary part. Okay, if you look into the dispersion relation, you will get to know that the intrinsic absorption coefficient of titanium is very large. Okay, so you can actually understand that the quality factor of the resonance of this localized surface plasmon resonance peak here is rather low, and that gives you this broadening of the absorption, and that is how and this is the difference between that gold discs and titanium discs, and why we actually opted for titanium discs here when we are planning to make a broadband absorber. Okay. So, once again we can attribute this broadband absorption to the combination effect of propagating surface plasmon and low Q localized surface plasmon resonance. Now, you can see here some of the parametric sweep result. It means like the influence of some parameters on the absorption performance and how the absorption spectra looks like for different materials. So, this one is a simulated result where D is the disc diameter that has been changed from 380 to 400 to 420 nanometer. The same thing is also seen experimentally, and you can see how it changes. So, they are sensitive to the dimensions as I mentioned. So, you can actually design the discs based on your requirement. Again, the periodicity is changed here, and the periodicity also tells you, it actually gives you the range over which you want to have this broadband absorption. So, here periodicity of 580, 600 and 620 nanometer has been studied, and simulated results and experimental results, they are very close to each other, right. And here also you can see, if you take the contribution to this absorption coming from gold and titanium, you can clearly see that titanium is contributing to the most of the absorption. So, that is the case here. This absorber is mainly based on this titanium nanodiscs. Now, we understood that how we can make narrowband, we understood how we can make broadband absorbers. Now, we have to understand how we can make ultra broadband metamaterial based perfect absorbers. When I say ultra broadband, I am thinking of a window something as large as 300 to say 4500 nanometer. So, it starts from typically UV, visible, near infrared, and then short and mid IR, something like that. So, it is typically catering to a very broad band, and this is the kind of structures we call them as ultra broadband absorbers. So, how do you make it? You can actually design them using 2D infinite array of hemi-ellipsoid shaped metallo-dielectric multilayer structures. So, here is the top view of that structure. So, this is the side view. So, you can see it is like a hemi-ellipsoid. So, half of the ellipsoid, and it is a alternating metal dielectric structure. So, it is based on a silicon substrate, but then you have a ground metal. Okay, it can be gold or silver. It has to be 300 nanometer. So, it blocks light completely and it will reflect. Okay, and then you have dielectric metal, you have these are the simulation setup basically with PML, perfectly matched layers. So, this allows you to do a simulation of this particular structure for TM polarization. Okay, here the H field is considered to be along y axis, and the wave propagation is considered to be along z axis. Okay, and port 1 is the excitation port, and port 2 is the other port. So, if you calculate S11, you can get the reflection characteristics, and if you calculate S21, you can find out the transmission characteristics from the S parameter matrix. Okay, and here is the periodicity P, that is basically the size D and the gap G between the hemi-ellipsoids. So, how many layers? We have considered 20 layers of metal dielectric alternate structures. Here molybdenum and germanium are considered, and not gold, we are using tungsten as a ground metal, and it is standing over a silicon substrate. Okay. So, a perfectly matched layer, as I mentioned, has been applied here on the top and bottom of the unit cell. So, this is the side view of the unit cell, this is the top view of the unit cell that you can see here. D is the diameter of this hemi-ellipsoid, the base diameter, that is 400 nanometer, and then gap is 20 nanometer. Okay, the periodicity is 420 nanometer, and these are the parameters that we have used, and other parameters are mentioned in this particular figure. I will not read out each of them. And then we have using the RF module of the COMSOL multiphysics software, the absorption spectrum has been calculated for 300 to 500 nanometer spectral window. Okay, and this allows one to get absorption, reflectance and transmittance for this structure at normal incidence. So, this is that particular structure, absorption, reflectance and transmittance, and as you can see here, the transmittance, the red one, is completely flat. So, there is zero transmittance across the structure, and you can also see that the absorption absorption is almost 100%, other than this few ringing effects that come from multiple resonance here. Okay, and more or less it is a very flat wideband absorption. Okay, and what is not absorbed is kind of reflected. So, the green curve shows you the reflection curve, and this is the plot for the two polarization, TE and TM polarization for normal incidence, and they are perfectly matching because the structure is also symmetric, right. So, this particular structure, as I mentioned, it is a ultra broadband metamaterial based perfect absorber, or this kind of absorbers are also called super absorbers because they give you almost 99% average absorption, and that is a big thing, 99% average absorption between 300 to 400 nanometer spectral range at normal incidence. And this particular spectral range, it comprises, as I mentioned earlier, UV, visible, near infrared, short wave and mid wave infrared wavelength. So, that is pretty wide range. Okay. So, this kind of metamaterial absorbers can be designed. Now, let us look into the applications of these metamaterial perfect absorbers. The first application that comes to our mind is solar energy harvesting. And when we talk about solar energy harvesting, the most important thing for us is to know that how the solar spectrum looks like. Okay, so you can see this is the solar spectrum or solar spectral radiation, okay, versus wavelength. So, it actually follows this particular pattern. Okay, so you can actually have a black body radiation, that black body radiation peaking around 5500, I believe. Okay, that can match this 5500 Kelvin. Okay, that can match this particular solar spectrum. But then what is important here is that it tells you the range over which you are supposed to absorb. Now, if you do not absorb anything beyond say 1800, you are not losing much, you are only having a very small portion of the solar spectrum which lies beyond 1800. So, you can actually design your absorber until here. Okay. There are many attempts basically in the literature to design this kind of perfect absorber. One such design has been published in this paper that I am showing here. So, this is a broadband absorber where you have a periodic square array of silica which are coated with iron film, okay, and this is separated from a bottom iron mirror by another silica film and a GST film. So, this is the 3D view and this is the 2D view of the structure. Again, you can calculate what is the spectral absorptivity of this structure. You can see that this structure can absorb very strongly from 400 to 2000, that is the entire band that we are looking for. Okay. Now, this is the absorption that is from this particular structure. Now, if we tweak this structure a little bit or you redesign this structure, your aim would be to have a flat absorption line over this entire window, and the discussion we had previously, those kind of structures can give you almost 100% of absorption over this band. Now, the question is why then we need to design this one again if that previous structure is giving us all that we need. Now, if you see the previous structure, fabrication wise that structure is very challenging. It is a hemispherical shape with alternating layers of metal dielectric, and then you have to maintain that reducing dimension as well. So, that is a very challenging structure. In comparison to that, this is much easier structure, and that can give you an average absorption of almost say 90% or so, 90 to 95%. So, in some cases where you do not have the facility to fabricate those complicated structures, you can still be happy with this kind of a structure. What are the other applications? So, this one is basically an application of a broadband metamaterial perfect absorber. Now, you can also have applications of narrowband metamaterial perfect absorbers as thermal emitters. Now, what are these thermal emitters? Now, if you think of a black body, it is basically an idealized body that can absorb all radiation which falls on it, and it re-radiates energy solely determined by its temperature as described by the Planck's law. Now, when you develop metamaterials, okay, and you are targeting an application of perfect absorber which exhibits the ability to have near uniform or near unity absorption in a frequency range, you are basically making it like a black body. So, this same material can also behave like a thermal emitter, right? Just like black body radiates, your metamaterial can also radiate. Now, according to Kirchhoff's law of thermal radiation, at equilibrium the emissivity of a material equals to its absorptivity. Therefore, in principle the metamaterial perfect absorbers can radiate energy as described by their absorptivity at a given temperature. Now, because of the resonant nature of the metamaterials, the perfect absorber, the narrowband perfect absorbers, they yield very sharp resonances with high absorption. That means they will basically act as very high Q thermal emitters, and they will also have very high emissivity. So, that way you can actually make very high Q high emissivity thermal emitters. So, here is one design of infrared metamaterial absorber that will also work as a thermal emitter. We will see that. So, here is the structure. First you start with a plus type, okay, plus kind of a structure. So, this is a metallic structure, gold structure on a dielectric, and on the back side also you have another gold layer, okay. So, this is the top view of the single band metamaterial absorber, and these are the dimensions, okay, all are in microns here, length, width, periodicity all are given, okay. And this is a dual band. So, this is basically a mixture of the small and the large. There are two structures which resonate at two different frequency bands, and that is why it is called a dual band metamaterial absorber, and the dimensions are given here, all are in microns again. And these two shows the top view, these two figure shows the perspective view, and in the two cases the thickness of the dielectric spacer is 0.2 micron here for the single band metamaterial absorber, and it is 0.3 micron in the case of dual band metamaterial absorber. Now, when you do the experimental absorption study of this structure, so here in the inside you can see the ACM images. So, for the single band structure you get this peak which is pretty good, and also these are all experimental pictures, okay. For the dual band you get these two bands which are absorbing very strongly, right. So, that way you can also compare the experimental absorptivity with the emissivity, and you see that they do follow the law of Kirchhoff that we have discussed, that the absorption pattern is same as their emission spectrum, right. So, that way you can actually see that you can develop a thermal emitter, a high Q thermal emitter at a single band, a dual band, or multiple bands depending on the design of your metamaterial absorber. Okay. So this one shows the absorptivity and emissivity of a single band absorber, or you can say emitter, whereas this one shows a dual band absorber or emitter. Okay. So that way you can actually design the materials. So what is important here is to understand that the structures, the emission spectrum is completely dependent on the structure that you are designing. Okay. If you choose a different shape, if you choose a different material, if you choose a different periodicity or a thickness, the resonance peak can be changed. If you want to play with the Q factor of the resonance, you can choose, if you want to lower high Q, okay, means you want a sharper resonance peak, you should select materials which are less lossy, and then if you want a resonance with a broader Q, okay, you should actually choose materials with high loss, that we have seen. Now, while choosing the material properties, you got to be very careful about the dispersion. So you have to choose the material property that is suitable for the range, the frequency range that you are considering. So usually there are websites like refractiveindex.info where you can download and see the dispersion curves of different materials, and that helps you understand which material could be useful in designing what kind of emitters at what frequency band. Okay. So with that, I think we have covered the topics, and that's all for this lecture. We will consider the topics of super lens and hyper lens in the next lecture. And in case you have got any queries on this particular lecture, you can drop an email to this email address with book in the subject line. Thank you.